In this example, we have the same Rankine cycle that we saw in the last example, except this time it's no longer ideal. We now have assigned a 75% isentropic efficiency to the turbine and an 85% isentropic efficiency to the pump. And in this example, we're going to go through and fix all of the states. So we're going to find the enthalpy value at every state. And then once we have those values, the analysis for turbine work or net work or Q in or Q out, any of that stuff will be exactly the same. Okay, so you'll see some remnants left over from the last example, and we're going to go through and understand why I've removed some of the things I have removed and fill in the correct values in light of this new information on the isentropic efficiencies. Okay, so let's turn our attention up here to the TS diagram. All right, so we have a saturated vapor entering the turbine at state 1, and in an ideal cycle, we have no change in entropy between state 1 and state 2. Now this cycle is not ideal anymore, so this state we're down here, we're going to call this state 2S. The real process is going to end with some greater entropy at state 2. Okay? And so we're connecting 1 and 2 with a dotted line here because we don't know what the details of that path are. All right, so state 2 to state 3, we're going to cool the fluid as before so that we have a saturated liquid entering the pump. In an ideal pump, of course, we would come straight up to the next isobar at 14 megapascals as before. This ideal process is going to connect states 3 and states 4S. The real process, because now we have an isentropic pump efficiency, is going to travel from state 3 to the real state 4. Okay? And then again, we have our path from 4 back to 1. So, in red now, let's trace the path of the cycle of interest in this problem. So 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Okay. So, now let's look at our state data. So nothing will have changed about state 1, right? The performance of the turbine doesn't affect the fact that I have a saturated vapor at 14 megapascals. At state 2, I have drawn my diagram assuming that I have a saturated mixture at state 2, but if I had a ton of irreversibilities in the turbine, I might actually kick state 2 outside the dome at 8 kilopascals. We're going to see below that we do in fact have a saturated vapor, a saturated mixture at state 2, but that may not always be the case. Okay? This time, the entropy at state 2 is not equal to the entropy at state 1. Now, at state 3, nothing has changed. I still have a saturated liquid at 8 kilopascals, and I do have a compressed liquid at 14 megapascals at state 4, but again, S4 does not equal S3 anymore. Okay, so now let's go down here. You'll recognize this work from the last example where we found the quality of state 2 and the enthalpy at state 2, but this was for an ideal Rankine cycle. So now we have found the quality of state 2S and the enthalpy at state 2S. Okay? So that's important to note, and what we can do now is use these values, use this value of enthalpy to find H2 rather than H2S. Okay, so recall that your isentropic turbine efficiency is equal to H1 minus H2 over H1 minus H2S. But of course, nothing special about these numbers. That just happens to be how our cycle is labeled. And when you're trying to figure out which difference you should put in the numerator versus the denominator, remember that the larger value should always be on the bottom. So there's going to be a bigger drop between H1 and H2S for an ideal turbine than between H1 and H2 for the actual turbine. All right, so doing a bit of rearranging now, we can write this equation for H2. So H1 I know from before, 2637.6 kilojoules per kilogram. I was told my turbine has an isentropic efficiency of 75%. And of course H2S now is that ideal enthalpy, or the enthalpy at my ideal state 2S, which was 1677.6. Okay, so now my actual value of enthalpy at state 2 is 1917.6 kilojoules per kilogram. So you'll note because the enthalpy leaving the turbine is a bit higher now, I'm not able to extract as much work from the turbine as I would have been able to do before. Okay, so now I can come up here and plug that value in to my, we'll call it property area. All right. Okay, so now let's look at the work that we did previously to find H4. All right, so we assumed that there was no entropy change and formed this convenient relation, which you will have seen in lecture. But we were doing that for an ideal pump. So this now represents H4S. Okay. Now my isentropic pump efficiency is defined differently than what we do for turbines. Again, the bigger value or the bigger difference needs to be in the denominator. Okay? So this is now ideal over actual. Okay, so let's rearrange this now such that we can find H4. Oh, getting ahead of myself here. There we are. So 187.93 is the value that I had before, so I'm just bringing that down. There's my isentropic pump efficiency, 85%, and that gives me a value of enthalpy of 190.4. So, because my pump has internal irreversibilities, the enthalpy leaving the pump is going to be higher. So some of those irreversibilities have produced some heat inside the pump and raised the enthalpy a little bit more than it would be otherwise. So if we were to find the corresponding temperature of H4 versus H4S, we would see a little increase with H4. Okay, so now that we have defined all the enthalpies for every state, we can proceed with an analysis just like we would have before. So the enthalpies that I would use to find turbine work or pump work or heat input, all of those are now these. Okay, we can, once we've defined all the enthalpies at all of our states, we can ignore the ideal states, in this case state 2s and state 4s.